Well, hey there. Welcome back to my YouTube channel. Thanks for joining me here today. I wanted to talk about this New Scientist article, which one of our listeners here, Julie, calls the Unireverse article, which is a funny way to put it. A couple weeks ago, I did a video about this article in New Scientist that said that researchers in Antarctica at the Anita experiment, this kind of antenna that they float over the ice, had detected these particles which indicated a universe, parallel universe to ours, going backwards in time. And this has caused quite a stir, as you can imagine. This is the link to the YouTube video I did about that article, and it's still the #1 trending article on New Scientist as of this morning. So it's made a lot of waves, and then a lot of tabloids picked it up. Well, a couple, 2 in the UK, even the New York Post did a story about it. And of course, they overdid it to some extent. They said that researchers had found evidence of a parallel reality in Antarctica, and it's not quite that. They found the energy signature of a heavy neutrino, high energy neutrino, which doesn't fit with the standard model that we have of physics, and it may be indicative of a particle that researchers have been searching for, which would indicate a dark matter universe next to ours. Now, because this particle was coming up from the Earth instead of going down, where neutrinos coming from outer space down towards the Earth, and it's a heavy neutrino, so it can't usually go through the Earth very often without hitting into something, and they detected this a couple times. They thought maybe this is indicative of a universe that goes backwards to ours. Now, to a lot of people, that may seem like incredible. Like, you know, we've talked about parallel realities here and multiverse theories, but the idea of one that's going backwards, you know, I mean, it's like, seems like science fiction. And we had a couple articles in Forbes magazine, of all places, from Jamie Carter and Ethan Siegel, 2 science writers, on back-to-back days, May 21st and 22nd, really making fun of the tabloids kind of going overblown on this story. But then they went further to ridicule the whole idea of parallel realities and multiverse theory, and that's where I think they're wrong. And the reason I know they're wrong is because there's a 100-year research tradition, starting with Paul Dirac, the famed Nobel Prize-winning physicist, who speculated before we could detect them that there would be particles of antimatter and other particles that quantum mechanics hadn't discovered yet, just from the equations of quantum mechanics, and he turned out to be right. So we know that there is other particles and other aspects of the universe that we can't see and we can't detect them yet, but our theory suggests they should be there. And that's what this Anita heavy neutrino, the tau neutrino, is all about. Around the time of Dirac, physicists, astrophysicists were looking at the idea of dark matter. Fritz, Zwicky saw it in local galaxies. You know, this force that holds galaxies together is not enough matter in our known universe, so it's called dark matter. And then Vera, Rubin reformulated this idea for the universe as we know it, which with many more galaxies, in the 1970s. So dark matter is something that's been around for a while. I learned about this at the University of Arizona. There was a great astrophysics program when I was a graduate student there in the 80s. I was a grad student in sociology, but the astrophysics lectures there at the planetarium every week were so fascinating. I always went, and they talked about the discovery of dark matter. I don't even think dark energy had been discovered yet, but that came along later in the 90s, this unknown force that pushes everything apart, galaxies away from each other. You know, one force pulls them into each other, dark matter, dark energy. Well, folks, dark energy and dark matter make up at least 90% of the universe, if not more. So we don't even know where we are. Most of the matter and energy around us has never been detected. Oh, it's been detected gravitationally, but we can't detect it any other way. That's why it's called dark energy and dark matter. Well, the point is, people have been speculating since Dirac, Yang and Lee, who we mentioned in a previous video, the video about the experiments at Oak Ridge, which we'll get to in a second, they've been speculating that there's a hidden sector. That's what Yang and Lee called it, because of something called charge parity time symmetry, that if you find particles of one type here, you should find the exact opposite particles, mirror image particles, also in our universe. But we don't find right-handed neutrinos, for example. And Yang and Lee speculated that this charge parity violation may be explained by a hidden sector. So you had Paul Dirac talking about phantom particles, antimatter particles that hadn't been detected then, just from the theory of quantum mechanics. You had Yang and Lee talking about a hidden sector. We had dark energy, dark matter, now dark energy. And people have been wondering, physicists and astronomers, astrophysicists, for over 100 years, where's the rest of this matter? And that's where the ANITA results fit in, is because folks like Neil Turek at the Perimeter Institute of Theoretical Physics in Canada have been speculating that there might be a particle, not a new particle, but an existing particle, if you have to know exactly 500 million billion volts, electron volts, in energy, that would account for 5 times as much matter, the dark matter, that we haven't been able to detect. And it turns out that this ANITA particle is exactly that energy level that Turek and others were speculating. And that's why this is such an interesting result, because there's a backstory here. There's a whole legacy of looking for this dark matter, dark energy, missing particles, hidden sectors, and so forth. And that's where all these ANITA results fit in. Now, it doesn't definitively show that there's a parallel universe there. I have to agree with Siegel and Carter on that. But it is the right way to look at things. And that's why I think the New Scientist article is very important. It's important because it shows us that you could have theories which, before any evidence is detected, say, hey, there should be something going on here that explains this mystery that we can't figure out. And then someone detects a particle that dovetails with it perfectly. That's what happened in this case. Now, both Carter and Siegel argue that maybe these ANITA results are just mistakes, that they're some sort of measurement error or, mistaken identity of a particle or something like this. But that's what they said about the missing neutron experiments, and that was several decades ago, and it's still never been resolved. So it's always easy to say that a measurement or an observation that doesn't fit with your idea of reality is a mistake. And that can be true many times, but sometimes it isn't. But the reason that the Siegels and the Carters are the Forbes authors here, I think that they're off base, is because they neglected other research going on right now. And we've talked about it. In this video, I mentioned the research by Leo Broussard and others at Oak Ridge National Laboratory in Tennessee, former home of the Manhattan Project, a major government laboratory where they're looking for missing neutrons. Neutrons decay at different rates depending on how you measure them. And they should decay at the same rate. And one idea is that this so-called mirror universe, which people have been speculating about for 100 years, that these neutrons are going over there briefly and coming back. About 1 out of every 100 neutrons in our reality is getting shared with this other reality, a reality that has 5 times as much matter as our universe, which perfectly, again, explains dark matter. So there's another experiment going on looking to explain dark matter with atomic particles that don't seem to be here in the right amounts. So it's like 2 parallel experiments looking for parallel realities. And so you need to look at the ANITA results in a broader context here. Now, it could be, but I don't think both would be right. Either the dark matter is explained by Leo Broussard and these kind of time-sharing neutrons that go back and forth between our reality and a mirror universe, or these ANITA results with neutrinos, that this neutrino they found could be responsible for this dark matter. So it's probably one or the other, or maybe neither. But this is how science works, is you have ideas, you have experiments you're looking for. And I don't see any reason to be so cynical and negative about this. I mean, these comments I'm seeing from some of these authors ridiculing parallel realities and multiverses seems to be completely misplaced. It's like what Stanton Friedman used to talk about, the noisy, nasty negativists. Research by proclamation. I mean, I'm just going to ridicule it and make fun of it, Well, yeah, you could do that, and you can ignore 100 years of physics here. And what's the point of that? That's like going backwards. We need to build on existing research and ideas that have come along. If you look at the history of scientific discovery, people have ridiculed just about every new idea that's come along. I mean, think about it. Quasi-crystals, plate tectonics, black holes. Even Einstein didn't believe in the existence of black holes. And his general relativity theory led to them. That's why people later on said it had to lead to black holes, and they were discovered later. Now, in Siegel's article, he says, there are only 3 observations of this strange neutrino. That's not very much. But how many observations does it take to verify a theory? In the case of Einstein's general relativity theory, where he said that matter would bend light, it only took one observation, the eclipse of 1919, where it was seen that light was bending around the sun from a distant star. So that was one observation, and that's all you needed to verify general relativity theory. So you really only need one good observation. Now, in this case, is this observation proof of a parallel reality going backwards in time? No, but it certainly fits with some of the ideas of what you would expect if such a thing were to exist. And again, we're dealing with lots of research going back a century from Nobel Prize winning physicists who argue that such things should be possible. Now, just because it seems really weird and strange is not a good enough reason to reject it. I mean, the examples I just gave, almost every new scientific discovery at the time seems strange. Just the idea that there's one Earth alone is really weird for people that would have lived 500 years ago, because back then the debate was how many Earths were there. There was thought to be a water Earth and a smaller solid Earth that floated on this water Earth, and that's what led Copernicus to challenge the Ptolemaic idea that the Earth is, the Earth-centered version of the universe, because back then when they were debating of the water sphere and the solid sphere, well, which one was the center of the universe? It didn't make sense. And that's what led him to rethink the whole thing when we led to the heliocentric theory. So the point is, and you know this if you're watching my channel here, I mean, science is evolving, science is changing, and ideas that seem really strange and unbelievable at a certain time may seem very obvious and self-evident just 10, 20 years later. That's how it works. So the fact that these ideas seem really strange is not reason to doubt them. You have to look at the evidence. You have to look at the ideas behind it. And yeah, 1 or 2 results don't prove that we're next to a parallel reality that's going backwards in time. But it could be true, because people have speculated from the beginning that if you have our matter universe, there has to be an antimatter universe too for the Big Bang to make sense. It's not an idea to laugh at. It's just something to ponder and look at. Does the evidence that we're seeing now fit into that or not? And then sort of go from there. So that's my thoughts about it. I'm sure we're going to be seeing more experiments in this vein. Is, can we detect a parallel reality, a particular parallel reality at a particle level in physics? It's certainly something that's interesting, and I imagine there'll be more experiments like this in our future. So anyway, what do you think? I'm curious. Put your comments in the box below. Those are my ideas about it, but I'm sure you have your own ideas, and I'm curious to hear what you think. So let me know. Thanks for watching. We'll talk to you. Take care for now, and bye.